Sometimes, the most unsettling discoveries are not loud or dramatic. They don't arrive with explosions or sudden revelations. They appear quietly, hidden inside data, numbers, and light that has traveled across space for years before reaching us, and only after careful study do we realize that something we believed to be solid is no longer holding its shape. For a long time, astronomers thought they understood the basic story of how planets form. Not every detail, but the outline felt reliable. Disks of gas and dust, slow accumulation, predictable paths. With each new telescope, that story seemed to grow more confident. Worlds appeared where models said they should. Patterns repeated. Order emerged from chaos. Then the James Webb Space Telescope looked deeper, not just at where a planet is, but at what it is made of. And what it found was a world that refuses to align with the story we've been telling. Its composition, its environment, and its apparent history do not fit together in the way our formation models predict. According to everything we thought we knew, this planet should not exist in the form we see it. Before we continue, if you enjoy slow, thoughtful journeys through space, science, and the unknown, you're welcome to subscribe to Theories Before Sleep. These videos are made to be listened to calmly, without urgency, allowing ideas to unfold gently rather than demand attention. What follows is not a mystery in the traditional sense. There is no single secret waiting to be revealed. Instead, this is a story about limits, the limits of our assumptions, the limits of our models, and the moment when observation becomes more detailed than explanation. As we explore what James Webb discovered, we're not just learning about one unusual planet, we're learning how much more there is to understand about how worlds are born at all. Let's take this slowly and begin where the certainty first started to fade. For most of modern astronomy, the story of how planets form has been surprisingly consistent. Not simple, but consistent enough that scientists could look at a star system and predict, with reasonable confidence, what kinds of planets should exist there, where they should be located, and how they should behave. These ideas were built slowly, over decades, using observations of our own solar system, computer simulations, and later, data from thousands of exoplanets discovered around distant stars. At the center of this understanding is the protoplanetary disk. When a star is born, it doesn't emerge alone. It forms from a collapsing cloud of gas and dust, and the leftover material flattens into a rotating disk around the young star. Inside this disk, tiny dust grains collide and stick together. Over time, these grains become pebbles, then rocks, then planetesimals, and eventually full-size planets. This process is slow, chaotic, and inefficient, but it follows certain rules. Close to the star, the disk is hot. Volatile materials like water, methane, and ammonia cannot easily freeze there. Only metals and silicates can survive long enough to form solid cores. As a result, theory predicts that small rocky planets should form close to the star. Farther out, beyond what is called the frost line, temperatures drop enough for ices to exist. This allows much more material to accumulate, making it possible to form large gas giants with thick atmospheres of hydrogen and helium. This framework explains our own solar system remarkably well. Mercury, Venus, Earth, and Mars are small and rocky. Jupiter and Saturn are massive gas giants far beyond the frost line. Uranus and Neptune, even farther out, are ice giants rich in heavier compounds. For a long time, scientists assumed this general structure was common across the galaxy. Then exoplanet discoveries began to complicate the picture. Astronomers started finding hot Jupiters, massive gas giants orbiting extremely close to their stars, sometimes completing an orbit in just a few days. According to classic models, these planets should not be able to form so close to a star. The leading explanation became planetary migration, the idea that planets form far away and then move inward over time, pulled by interactions with the disk or with other planets. Migration helped patch the theory, but it also introduced new complexity. How fast does migration happen? How often does it stop? Why do some planets migrate while others remain stable? Each new discovery forced adjustments, but the core framework still held together. The planet revealed by the James Webb Space Telescope doesn't just stretch the models, it actively breaks them in multiple ways at once. Its location, composition, and atmospheric properties don't line up with what migration alone can explain. It's not just in the wrong place. It appears to be made of the wrong stuff, assembled in a way that current simulations struggle to reproduce at all. What makes this particularly unsettling is that Webb doesn't rely on indirect hints. Earlier telescopes often detected planets by their gravitational effects or by how they dimmed their stars. James Webb, by contrast, can directly analyze starlight that has passed through a planet's atmosphere, can identify molecules, measure temperature profiles, and reveal chemical signatures with unprecedented clarity. In this case, Webb detected an atmosphere that suggests formation conditions very different from what the planet's current orbit would imply. Certain ratios of carbon, oxygen, and other elements point to a birth environment that doesn't match its present location. In simple terms, the planet carries chemical fingerprints from a place it shouldn't have come from. This is where the problem becomes serious. If the planet formed where it is now, the disk should not have contained enough solid material to build a core large enough to capture such a thick atmosphere. If it formed farther out and migrated inward, the migration should have stripped or altered the atmosphere in ways that are not observed. If it formed through some rapid gravitational collapse, that mechanism contradicts other aspects of its structure. Each explanation solves one issue but creates another. What makes this discovery especially important is that it's not isolated. Webb is beginning to reveal a population of planets that occupy uncomfortable spaces between categories. They are too large to be terrestrial worlds, too small or chemically strange to be classic gas giants, and too close to their stars to fit standard timelines. Formation models that worked reasonably well before now feel incomplete. This forces scientists to confront a deeper issue. Most planet formation models were tuned to match a limited set of observations. They were never guaranteed to be universal. They were approximations built on the assumption that the processes seen in our solar system are typical. James Webb is showing us that typical may be a dangerous word. The telescope's sensitivity allows it to see atmospheres as they actually are, not as simplified averages. It reveals layers, gradients, and chemical disequilibria that older instruments blurred together. This means that many planets previously thought to be understood may in fact be far more complex than assumed. In the case of this particular planet, the mismatch between theory and observation isn't subtle, it's structural. The data doesn't merely suggest that parameters need adjusting. It suggests that entire pathways of planet formation may be missing from our models. One possibility is that planet formation is far more chaotic than previously believed. Instead of smooth growth inside neat disks, planets may frequently form through violent interactions, collisions, and rapid rearrangements. Another possibility is that disks themselves are more chemically diverse than assumed, allowing planets to assemble from very different building blocks even at similar distances from their stars. There is also the unsettling idea that timing matters more than location. A planet that forms very early, while the disk is still massive and turbulent, might capture materials that later become unavailable. A planet that forms late might inherit a completely different composition, even if it forms in roughly the same place. James Webb's data suggests that we cannot infer a planet's history from its present position alone. Location is not destiny. This challenges one of the most comforting assumptions in planetary science, that order emerges naturally from chaos. That given enough time, disks settle, planets find stable orbits, and systems become predictable. Webb is hinting that unpredictability may be the rule rather than the exception, and that has profound consequences. If planets can form in ways we don't yet understand, then our estimates of how common Earth-like worlds are may be deeply flawed. Worlds that appear promising based on size and orbit may have hostile compositions. Worlds dismissed as unlikely may turn out to be surprisingly complex. Habitability, already a fragile concept, becomes even harder to pin down. This first glimpse into a planet that breaks formation models is not a failure of science. It is science doing exactly what it is supposed to do, confronting reality when reality refuses to match expectation. James Webb didn't just find an unusual planet, it exposed the limits of our assumptions. And in doing so, it opened the door to a far stranger and more varied universe than we were prepared to imagine. When scientists first began to seriously confront what this planet implied, the discomfort didn't come from confusion alone, it came from recognition that the rules being broken were not minor guidelines but foundations, the kind of foundations that entire models rest upon. And when those foundations shift even slightly, everything built on top of them becomes uncertain. One of the most unsettling aspects of this planet is how confidently it contradicts expectations. It doesn't sit near the boundary of what models allow, it sits well outside them. Its mass, atmospheric composition, and orbital configuration don't just stretch probabilities, they occupy regions of parameter space that simulations rarely produce at all. This isn't a case of bad luck or rare coincidence. It suggests that our understanding of planetary birth is missing something essential. To appreciate why this is so disruptive, it helps to understand how formation models are constructed. Most are not built from first principles alone, they are calibrated. Scientists run simulations with adjustable parameters, disk mass, temperature gradients, dust composition, turbulence, and tune them until the outcomes resemble the planetary systems we observe. When new observations arrive, those parameters are adjusted again. Over time, the models become very good at reproducing what we already know, but that strength becomes a weakness when something genuinely new appears. James Webb didn't just add another data point, it added a contradiction that cannot be resolved by tuning a few numbers. The chemical fingerprints in this planet's atmosphere suggest formation conditions that don't align with any single region of the disk. Certain molecules imply cold origins, while others imply formation in much warmer environments. In traditional models, those conditions are separated by vast distances and long timescales. This raises a troubling question: how did those signatures end up together? One explanation being explored is that the planet may have assembled in stages, acquiring material from different regions of the disk at different times. But this idea quickly runs into practical issues. Material in protoplanetary disks doesn't move freely. It follows pressure gradients, interacts with magnetic fields, and is constantly influenced by the growing star. Moving large amounts of solid material across the disk without destroying or dispersing it is extremely difficult. Another possibility is that the disk itself was far more mixed than models assume. Instead of neat, layered regions with predictable chemistry, early disks may be chaotic, turbulent environments where material from different zones becomes thoroughly blended. If this is true, then the idea of clean frost lines and chemically distinct regions may be oversimplified. James Webb's observations lend some support to this. The atmospheric composition of the planet suggests chemical ratios that don't match what would be expected from a disk with well-defined boundaries. Instead, they point toward a history of mixing, disruption, and rapid change. This implies that disks may be chemically unstable environments, especially in their earliest stages. Timing then becomes critical. If a planet forms very early while the disk is still massive and chaotic, it may capture a chemical snapshot that no longer exists later. A planet forming just a few 100,000 years later might inherit a completely different composition, even if it forms in the same location. This introduces a level of historical dependence that most models don't fully account for. In other words, where a planet forms may matter less than when it forms. This idea challenges decades of thinking. For a long time, planetary science treated formation as a largely spatial problem. Distance from the star determined temperature, chemistry, and outcome. Time was important, but secondary. James Webb is suggesting that time and chaos may play a much larger role than previously thought. There is also the question of planetary migration, which until now has been the go-to explanation for misplaced planets. Migration explains hot Jupiters reasonably well, but the planet Webb observed doesn't fit cleanly into migration scenarios. Its atmosphere lacks certain features that would be expected if it had travelled through dense disk regions over long distances. Migration should leave scars, thermal signatures, altered chemistry, or mass loss that are not clearly present. This leaves scientists with an uncomfortable choice. Either migration behaves very differently than current models suggest, or this planet followed a formation pathway that doesn't involve classical migration at all. Some researchers have begun to revisit ideas that were previously considered fringe or unlikely. One such idea is disk instability, a process where parts of the disk collapse directly under their own gravity to form planets rapidly, without the slow buildup of a solid core. This mechanism can produce large planets quickly and in unexpected places. However, disk instability has its own problems. It tends to produce planets that are too massive and too chemically uniform. The planet observed by Webb doesn't fit neatly here either. Its mass is moderate and its atmospheric composition suggests more processing than a simple gravitational collapse would allow. Every explanation seems to fall short in a different way. This is where the discovery becomes transformative rather than frustrating. It forces scientists to confront the possibility that planet formation is not governed by a small set of dominant pathways, but by a wide spectrum of overlapping processes. Growth, collapse, migration, mixing, and collision may all play roles, with different combinations dominating in different systems. James Webb's strength is that it can see the results of these processes imprinted in planetary atmospheres. Atmospheres are historical records. They preserve clues about where a planet formed, what materials it encountered, and how it evolved. Unlike orbital positions, which can change dramatically over time, atmospheric chemistry often carries deep memory. The fact that this planet's atmosphere tells a conflicting story suggests a complex history that cannot be reduced to a single narrative. It likely experienced multiple formation phases, each leaving a partial imprint. That kind of history is difficult to simulate, but it may be far more common than we realized. There is also a philosophical shift happening beneath the technical debate. For decades, astronomers hoped that as more planets were discovered, patterns would become clearer and cleaner, that the universe would reveal a few dominant architectures repeated over and over. Webb is hinting at the opposite, that diversity, not uniformity, may be the defining feature of planetary systems. If that is true, then the goal of planetary science may need to change. Instead of searching for the typical planet or the standard formation pathway, scientists may need to embrace complexity and accept that exceptions are not rare outliers, but fundamental expressions of how nature works. This has direct implications for how we search for life. Habitability has often been defined using simple criteria: the right size, the right distance, the right star. But if formation histories can produce wildly different outcomes even under similar conditions, then habitability becomes harder to predict. Two planets that look similar on paper may be profoundly different in reality. James Webb's discovery does not answer these questions. It multiplies them, but that is precisely its value. Science advances not when models are confirmed, but when they are challenged in ways that cannot be ignored. This planet is not an anomaly to be brushed aside, it is a signal. A message that the universe is more inventive than our theories and less interested in fitting into neat categories. As more data arrives from Webb and future telescopes, scientists will need to rebuild their understanding of planet formation from the ground up, incorporating chaos, timing, and chemical diversity as central features rather than complications. The planet that breaks every formation model is not a problem to be solved quickly. It is an invitation to rethink how worlds come into being at all. As the implications of this planet began to settle in, scientists realized that the real challenge was not explaining one strange world, but understanding what its existence says about all the others. A single planet that defies formation models is interesting. The universe that produces such planets naturally is transformative. And that is where the conversation quietly shifts from anomaly to pattern. One of the first realizations was that the frameworks used to classify planets may be fundamentally incomplete. For years, planets have been sorted into neat categories: terrestrial planets, gas giants, ice giants, sub-Neptunes, super-Earths. These labels are useful, but they also imply boundaries. They suggest that planets occupy discrete boxes formed through distinct processes. James Webb's observations suggest that reality is far more continuous. Planets may slide across categories over time, assembling characteristics from multiple formation regimes rather than belonging cleanly to one. This planet appears to exist in that in-between space. It carries the mass of one class, the chemistry of another, and the orbital behavior of neither. That combination is difficult to reproduce, not because models are weak, but because they were never designed to produce hybrids. They assume that nature chooses one pathway at a time. Webb's data suggests that nature may not be so selective. This leads to a deeper question: are formation models failing because they are wrong, or because they are too tidy? Planet formation is often described as a sequence. Dust becomes rock, rock becomes core, core becomes planet. Gas accretes, orbits stabilize. But in a real disk, these processes may overlap, interfere, and restart. A growing planet may partially lose its atmosphere, then regain it. It may migrate inward, stall, then be pushed outward again. It may collide with other bodies, altering its internal structure long after formation is thought to be complete. James Webb's planet shows signs consistent with such a turbulent history. Its atmospheric composition suggests processing that would require multiple heating and cooling episodes. Some molecules appear intact that should have been destroyed by prolonged exposure to stellar radiation. Others appear enriched in ways that imply access to reservoirs of material not expected at its current orbit. This points to a formation history that is not linear but episodic. Another uncomfortable implication is that disks themselves may be less predictable than assumed. Protoplanetary disks are often modeled as smooth, gradually evolving structures. In reality, they are likely shaped by shocks, instabilities, magnetic fields, and rapid changes in accretion rates. These effects can create pockets where conditions differ dramatically from the average disk environment. In such a disk, planets may not form at well-defined distances, but within temporary niches that exist only briefly. A planet forming in one of these niches could acquire unusual properties that persist long after the disk itself has vanished. By the time we observe the planet, the environment that created it no longer exists, leaving behind a world that appears impossible when judged by current conditions alone. This idea reframes how scientists interpret exoplanet data. Instead of asking whether a planet makes sense given where it is now, they must ask whether it could have made sense at any point in the system's early history. That shift sounds subtle, but it dramatically expands the range of plausible explanations. James Webb's strength lies in its ability to probe atmospheres with unprecedented precision. By measuring absorption features across a wide range of wavelengths, it reveals not just what molecules are present, but how they are distributed and how they interact. This allows scientists to infer temperature gradients, atmospheric circulation, and chemical disequilibrium. In this planet's case, those details matter. The atmosphere does not appear to be in simple equilibrium. Certain molecules coexist in ratios that suggest ongoing or recent processes that maintain them. This hints at internal heat, dynamic mixing, or even residual accretion of material long after formation. Such complexity undermines the idea that planets quickly settle into static states. Instead, planets may remain chemically and physically active for much longer than previously thought. Their atmospheres may evolve in response to internal and external influences in ways that blur the line between formation and evolution. There is also the question of observational bias. For years, astronomers relied on limited data sets that favoured certain types of planets. Those biases shaped theory as much as observation. James Webb is now revealing planets that would have been invisible or mischaracterized before. This raises the possibility that formation models were never truly universal, but tailored to a narrow slice of planetary diversity. If so, then the planet that breaks every model may not be rare at all. It may simply be one of the first clearly seen examples of a broader class of worlds that were previously hidden. Webb's discovery could be less about an exception and more about a revelation. This realization carries a humbling message. Human understanding of planetary systems has been built on a foundation of limited perspective. Even with thousands of known exoplanets, the details that truly matter were often beyond reach. We saw shadows, not structures. Webb is now illuminating those structures, and they are more complex than anticipated. There is a parallel here with earlier moments in astronomy. When telescopes first revealed that the Milky Way was not the entire universe, but one galaxy among billions, it didn't invalidate physics, it expanded it. When quantum mechanics revealed that particles behave in probabilistic ways, it didn't destroy classical mechanics, it showed where classical intuition breaks down. This planet occupies a similar role. It marks a boundary where existing intuition about planet formation stops being reliable. Scientists are beginning to respond by developing models that embrace variability rather than suppress it. New simulations incorporate stochastic processes, chaotic disk behavior, and feedback loops that allow planets to influence their own formation environments. These models are computationally expensive and harder to interpret, but they may be necessary to capture the richness revealed by Webb. At the same time, there is caution. Extraordinary claims require careful validation. Researchers are reanalyzing the data, testing alternative interpretations, and waiting for additional observations. Webb's measurements are powerful, but they are not infallible. Subtle assumptions about cloud formation, atmospheric dynamics, or stellar activity can influence conclusions. Yet even with conservative interpretations, the tension remains. What makes this discovery especially compelling is that it arrives at a moment when planetary science is poised for transformation. Webb is not alone. Upcoming telescopes and missions will expand the sample size, allowing scientists to see whether this planet is truly unusual or part of a continuum. If similar planets are found, the pressure to revise formation theories will become unavoidable. There is also a psychological shift underway. For a long time, scientists hoped to find comfort in patterns. Patterns imply predictability, and predictability implies understanding. Webb's planet suggests that understanding may require accepting a certain level of unpredictability as fundamental. This does not mean abandoning theory, it means redefining its goals. Instead of seeking a single dominant pathway, scientists may need to describe a landscape of possibilities, where outcomes depend sensitively on initial conditions, timing, and chance interactions. In such a landscape, planets that should not exist are not errors. They are natural products of a universe that does not simplify itself for our convenience. James Webb's discovery invites us to see planet formation not as a factory process with standardized outputs, but as a creative, chaotic phenomenon where diversity is not a bug but a feature. Worlds may emerge with properties shaped by unique histories, carrying signatures that resist easy classification. As this realization takes hold, the planet that breaks every formation model becomes something else entirely. Not a problem to fix, but a clue. A clue that the universe is far more inventive than the stories we have told about it so far. As the implications of this discovery continue to unfold, another layer of tension becomes clear. The challenge is no longer just theoretical, it is observational. James Webb has given scientists a level of detail that exposes inconsistencies not only in models, but in the assumptions behind how data itself is interpreted. When older telescopes produced ambiguous signals, models could absorb uncertainty. Webb's clarity removes that shelter. One of the most unsettling aspects is how confidently the atmosphere of this planet speaks. Atmospheric chemistry is not easily fooled. Molecules form, persist, and interact according to physical laws that are difficult to bypass. When James Webb detects specific ratios of carbon-bearing and oxygen-bearing molecules, those ratios point directly to the conditions under which the planet assembled its atmosphere. They act like a chemical memory, encoding temperature, pressure, and location at the time of formation. In this case, that memory is inconsistent. Some of the detected molecules suggest formation in cold regions of the disk, where ices dominate, and oxygen-rich compounds should be abundant. Others suggest a warmer origin, where volatile ices would have evaporated and carbon-rich chemistry would be favoured. In standard models, these environments are separated not only by distance, but by time. A planet should not be able to sample both without leaving obvious traces of disruption. Yet the atmosphere does exactly that. This forces scientists to reconsider how stable atmospheric signatures really are. It was once assumed that once a planet's atmosphere settled, it largely preserved its original composition unless dramatic events occurred. Webb's data suggests atmospheres may be far more dynamic, capable of incorporating new material or undergoing chemical reshaping long after formation. If that is true, then atmospheres are not just records of birth, but living systems that evolve alongside their planets. That realization complicates interpretation, but also enriches it. Instead of a single snapshot frozen in time, an atmosphere becomes a layered history where different epochs leave overlapping traces. This raises a difficult question. How much of what Webb sees reflects where the planet formed, and how much reflects what happened to it afterward? The answer matters deeply. If atmospheres can change significantly after formation, then many assumptions about exoplanet origins may need to be revisited. Migration, impacts, stellar radiation, and internal heating could all reshape atmospheric chemistry in ways that mimic formation signatures. Disentangling these effects becomes a delicate process. James Webb provides clues, but not certainties. What makes this planet particularly disruptive is that multiple lines of evidence point toward contradiction simultaneously. The orbit suggests one history, the mass suggests another. The atmosphere suggests several more. When different data sets disagree, it usually means a hidden variable is at work. Something important is missing from the picture. Some researchers suspect that early stellar behavior may play a larger role than previously appreciated. Young stars are not stable, gentle objects. They flare, emit intense radiation, and undergo rapid changes in luminosity. A planet forming during this chaotic phase may experience conditions that are rarely modelled accurately. If intense radiation strips part of an atmosphere early on and later accretion replenishes it, the resulting composition could look paradoxical. If stellar winds push material around the disk unevenly, planets could accrete chemically diverse material without migrating long distances. These processes are difficult to simulate but may be common. There is also growing interest in the role of planetary collisions. Collisions are often treated as catastrophic endpoints, but they may be formative rather than destructive. A planet that experiences multiple impacts could acquire new material, alter its internal structure, and reset its atmosphere. Depending on timing, such impacts could create hybrid chemical signatures that defy simple classification. James Webb's data does not directly show collisions, but it does not rule them out either. In fact, some atmospheric features could be consistent with shock heating or post-impact chemistry. This suggests that violent events may be integral to planet formation, not rare exceptions. Another emerging idea is that planets may not form alone. In crowded disks, multiple embryos can grow simultaneously, interacting gravitationally and exchanging material. A planet that ultimately survives may incorporate fragments of others, blending histories into a single body. Such a planet would naturally resist clean categorization. This perspective reframes the discovery in a profound way. The planet may not be strange because it formed incorrectly. It may be strange because it formed collectively. James Webb's observations push scientists toward a more holistic view of planetary systems, one where interactions matter as much as initial conditions. Instead of isolated objects forming independently, planets may be products of complex ecosystems shaped by feedback loops and shared environments. This has implications beyond formation theory. It affects how scientists estimate planet populations, system stability, and long-term evolution. If formation pathways are more diverse than assumed, then statistical models of exoplanets may need to be rebuilt from scratch. There is also a psychological element to this shift. Scientific models often reflect a desire for elegance and simplicity. Clean rules are easier to teach, easier to simulate, and easier to trust. Webb's planet resists elegance. It suggests that nature may favor richness over simplicity, and that understanding may require embracing messiness. This does not diminish the power of science, it deepens it. Throughout history, major advances have come from moments when observations refused to fit established frameworks. The orbit of Mercury challenged Newtonian gravity. Black body radiation challenged classical physics. In each case, the response was not to discard observation, but to expand theory. James Webb's discovery may represent a similar inflection point for planetary science, not a crisis but an opportunity. Already, researchers are proposing new frameworks that treat formation as a probabilistic process rather than a deterministic one. In these models, planets emerge from distributions of possible outcomes shaped by local conditions, timing, and chance. Instead of predicting exact configurations, the goal becomes mapping ranges of possibility. Within such a framework, a planet that breaks every formation model is no longer an anomaly. It is an expected outcome of a universe that explores many possibilities simultaneously. This shift has a subtle but important consequence for how humanity views its place in the cosmos. If planet formation is wildly diverse, then the conditions that produced Earth may be less typical than hoped, but also less unique than feared. Earth becomes one expression among many, shaped by a particular chain of events rather than a universal template. James Webb's planet does not threaten the search for understanding, it expands it. By exposing the limits of existing models, it invites scientists to look deeper, think broader, and accept that the universe may not conform to our preferences for order. It reminds us that theories are tools, not truths, and that reality is always more intricate than the stories we tell about it. As more worlds like this are revealed, the question will no longer be whether planet formation models need revision. That will be taken for granted. The real question will be whether we are ready to accept a universe where formation is not a script, but a conversation between physics, chance, and time. And James Webb, quietly observing from far beyond Earth, is making sure we cannot ignore that conversation any longer. As scientists absorb the full weight of what this planet implies, attention begins to shift from explanation to consequence. Not just consequences for theory, but for how planetary science understands uncertainty itself. Until now, uncertainty was treated as a temporary gap, something that more data would eventually erase. James Webb is suggesting something more unsettling. That uncertainty may be a permanent feature of how planets form, not a flaw in our measurements. This planet forces a re-evaluation of how confident scientists can be when linking cause and effect in planetary histories. For decades, models relied on relatively clean inputs and outputs. Given a disk of a certain mass and composition, orbiting a star of a certain type, one could predict the likely outcomes. The discovery now challenges that confidence by showing that identical starting conditions can lead to radically different results. In other words, planet formation may be sensitive to small differences in ways that amplify over time. This sensitivity is familiar in other areas of physics. In chaotic systems, tiny variations in initial conditions can lead to dramatically different outcomes. Weather is a classic example. Planet formation, it now seems, may behave similarly. Two disks that appear nearly identical in mass, temperature, and composition may produce entirely different planetary architectures depending on subtle fluctuations that are impossible to measure after the fact. James Webb's planet may be the first clear observational hint that planetary systems are chaotic systems in the strict physical sense. If that is true, then the idea of predicting exact outcomes becomes unrealistic. Instead, science must focus on probability, distributions, and ranges of behavior. This is a profound shift. Rather than asking, what kind of planet should form here, scientists may need to ask, what kinds of planets could form here, and how likely is each outcome? The difference is subtle but transformative. It replaces certainty with expectation, and prediction with statistical understanding. The atmosphere of this planet plays a crucial role in driving this shift. Its chemical complexity cannot be explained by a single formation pathway, and that complexity is not random. It follows physical laws, but those laws interact in ways that produce multiple possible histories. The atmosphere becomes evidence not of a unique event, but of overlapping processes unfolding over time. This realization forces scientists to confront a difficult truth. Some information about a planet's past may be fundamentally unrecoverable. Even with perfect instruments, certain details may be lost to time, erased by mixing, evolution, and chance. James Webb shows us more than ever before, but it also reveals the limits of what can be known. This does not weaken science, it clarifies its boundaries. Another consequence of this discovery is a reassessment of how planetary systems evolve after formation. It was once assumed that once a planet settled into a stable orbit with a stable atmosphere, its major characteristics were largely fixed. Webb's data suggests that planets may remain open systems for far longer, exchanging material, energy, and momentum with their environments in subtle ways. Atmospheres may be replenished, altered, or partially stripped multiple times. Internal heat may drive chemical reactions long after formation. Stellar radiation may reshape surface and atmospheric conditions continuously. The planet observed by Webb appears to carry traces of such long-term evolution, making it difficult to draw a clear line between formation and maturity. This blurring of stages complicates classification but enriches understanding. Planets are no longer static outcomes of early events. They are dynamic entities with histories that unfold over billions of years. There is also a methodological consequence. Traditionally, models were validated by their ability to reproduce observed planets. But if observed planets are more diverse than models anticipate, validation becomes more challenging. A model that produces many outcomes may appear less precise, but it may be more realistic. James Webb is pushing planetary science toward a philosophy that values robustness over precision. A good model may not predict exact outcomes, but it should accommodate diversity without breaking. The planet that breaks formation models reveals which theories are brittle and which are flexible. This distinction matters beyond academic interest. Planet formation models underpin estimates of how common different types of worlds are. Those estimates influence everything from mission planning to public expectations about life elsewhere in the universe. If models systematically underestimate diversity, they may also underestimate possibilities. At the same time, this discovery invites humility. For years, planetary science benefited from a relatively orderly picture. Systems could be compared, categorized, and ranked. James Webb is showing that order may be an illusion born of limited resolution. With clearer vision comes complexity. There is also an emotional dimension to this shift. Scientists, like all humans, form attachments to elegant ideas. A clean theory that explains many observations is satisfying. Letting go of that elegance can be uncomfortable. The planet Webb observed does not politely ask for minor revisions. It demands reconsideration. Yet history shows that such moments are fertile rather than destructive. When astronomers realized that galaxies exist beyond the Milky Way, the universe did not become less understandable. It became larger. When physicists accepted that time and space are relative, reality did not become meaningless. It became richer. Planetary science now stands at a similar threshold. Another consequence of this discovery is its effect on interdisciplinary research. Understanding this planet requires collaboration between astronomers, chemists, physicists, and computational scientists. No single discipline holds all the answers. The complexity revealed by Webb encourages cross-disciplinary thinking, blending insights from fluid dynamics, thermochemistry, and chaos theory. This collaborative shift may be one of the most lasting impacts of the discovery. It changes how questions are framed and how solutions are sought. Instead of searching for a single explanation, scientists explore networks of interacting causes. There is also a lesson here about the nature of progress. Scientific advancement is often imagined as a steady march toward truth. In reality, it is punctuated by moments where progress feels like regression. Models that once seemed secure suddenly appear fragile. Confidence gives way to doubt. James Webb's planet represents such a moment. It forces planetary science to pause, reassess, and rebuild. That process may take years, even decades, but it will produce a deeper, more resilient understanding. This discovery also influences how future observations are planned. Instead of targeting planets that fit expectations, astronomers may increasingly seek out those that challenge them. The unusual becomes valuable, the outlier becomes informative. James Webb is uniquely suited to this role because it does not merely detect planets, it characterizes them. It reveals complexity rather than averaging it away. This makes it a tool not just for confirmation, but for disruption. As more data accumulates, the planet that breaks every formation model may no longer stand alone. It may become the first recognized member of a broader class of worlds that defy simple explanation. If that happens, the narrative will shift again from surprise to acceptance. What this planet ultimately teaches us is not that our theories are wrong, but that they are incomplete. They capture certain aspects of reality while overlooking others. James Webb is filling in those gaps, not with answers, but with questions that cannot be ignored. In doing so, it reminds us of something fundamental about science. Understanding grows not from comfort, but from confrontation with the unexpected. The universe does not owe us simplicity, it offers complexity, and challenges us to rise to it. The planet that breaks every formation model is not an endpoint in this story. It is the beginning of a new chapter, one where the universe is allowed to be as intricate as it truly is. As the scientific community continues to grapple with what this planet represents, attention begins to drift toward an even deeper implication, one that goes beyond formation models, beyond atmospheres, and even beyond planets themselves. The discovery is forcing astronomers to confront a limitation that is rarely acknowledged openly: the idea that our theories may be shaped as much by human expectations as by physical reality. For a long time, planet formation models have been built around a subtle assumption that nature prefers efficiency, that systems evolve towards stable, predictable configurations, that disks smooth out, that chaos fades, and that what remains is orderly and classifiable. This assumption was never written explicitly into equations, but it guided how models were interpreted and refined. When observations didn't match expectations, they were treated as noise or as rare exceptions. James Webb's observations challenge that assumption directly. The planet in question does not look like a system that's settled down. It looks like a system that remembers its turbulence. Its properties suggest that disorder was not merely a transitional phase, but a defining feature of its formation. This forces scientists to ask whether chaos is not something planets escape, but something they inherit. If that is true, then the diversity of planets in the universe may not be something to be explained away. It may be the natural outcome of a process that never truly stabilizes. Planetary systems may carry the fingerprints of their birth environments indefinitely, even billions of years later. This idea has profound implications for how scientists interpret not just unusual planets, but ordinary ones as well. A planet that appears normal by current standards may simply be one whose chaotic history happened to align with expectations. Another planet, formed under slightly different conditions, may appear exotic despite obeying the same physical laws. James Webb's discovery suggests that what we call normal may be a statistical illusion. This realization also changes how scientists think about failure in modeling. Traditionally, a model that cannot reproduce an observation is considered incomplete or incorrect. But if planetary systems are inherently chaotic, then failure to predict specific outcomes may not indicate a flawed theory. It may indicate that prediction itself has limits. In such a universe, theories are not meant to forecast exact results, but to define boundaries within which many outcomes are possible. James Webb's planet appears to exist comfortably within physical law, but outside our expectations of regularity. This forces a philosophical shift. Instead of asking why the planet violates formation models, scientists must ask why they expected the models to be so restrictive in the first place. Another layer of consequence emerges when considering how planetary science communicates uncertainty. For decades, public narratives about exoplanets emphasize clarity and progress. Planets were counted, categorized, and ranked. Each discovery seemed to bring us closer to understanding our place in the universe. Webb's planet complicates that narrative by showing that more knowledge does not always produce simpler answers. Instead, it produces better questions. This is not a setback, it is a maturation of the field. Planetary science is moving from an era of discovery to an era of interpretation. Webb's data is so rich that interpretation becomes the central challenge. Understanding how to read complexity without oversimplifying it is now the frontier. There is also a technical dimension to this shift. Models that embrace chaos, variability, and feedback are computationally demanding. They require simulations that run for long periods, explore vast parameter spaces, and accept that many runs will produce wildly different outcomes. This is a departure from earlier approaches that sought convergence and stability. James Webb's planet makes such approaches unavoidable. If simple models fail, then complexity must be confronted head-on. This has ripple effects across the field. Funding priorities shift. Computational resources are reallocated. Training emphasizes interdisciplinary thinking. Young researchers are encouraged to think in terms of systems rather than isolated processes. The discovery is not just changing what scientists study, but how they study it. There is also an emotional undercurrent to this transformation. Scientists are trained to be cautious, skeptical, and precise. Embracing uncertainty can feel uncomfortable, even threatening. Yet the most enduring advances in science often come from moments when uncertainty is acknowledged rather than resisted. James Webb's planet embodies such a moment. It also reframes the role of observation. Webb is not merely confirming predictions. It is acting as an agent of disruption, revealing structures and patterns that theory did not anticipate. This reverses the traditional hierarchy where theory leads and observation follows. Now, observation is leading theory into unfamiliar territory. This shift echoes earlier revolutions in astronomy. When Galileo pointed his telescope at the sky, he did not confirm Aristotelian cosmology. He shattered it. When Hubble measured galactic redshifts, he did not refine existing models. He expanded the universe itself. James Webb's discovery may represent a similar turning point, not in scale, but in complexity. Another consequence of this planet's existence is how it influences the search for life. Habitability has often been framed in terms of location, the so-called habitable zone. But if planets conform with wildly different compositions and histories even within similar zones, then habitability becomes harder to predict. A planet may sit at the right distance from its star but have an atmosphere shaped by violent early processes that render it inhospitable. Another planet outside traditional zones may retain conditions suitable for complex chemistry due to an unusual formation history. James Webb's planet suggests that history matters as much as geometry. This realization encourages caution. It tempers optimism without extinguishing it. It reminds scientists that life-friendly conditions may arise in unexpected places, but also that appearances can be misleading. There is also a subtle implication for how humanity understands itself. For a long time, Earth was seen as either typical or exceptional. Each discovery pushed that perception one way or the other. Webb's planet suggests a third option. Earth may be neither typical nor uniquely special. It may be one outcome among many in a universe that produces a vast range of planetary stories. That perspective is both humbling and liberating. It frees humanity from the need to see itself as central, while also affirming that complexity and contingency are fundamental features of existence. James Webb's discovery does not diminish the beauty of planetary systems, it enhances it. A universe that produces only predictable outcomes would be simpler but less interesting. A universe that produces planets with unique, irreducible histories is richer, even if it resists easy explanation. As scientists continue to analyze the data, debate interpretations, and refine models, one thing becomes increasingly clear. The planet that breaks every formation model is not an inconvenience, it is a gift. It forces planetary science to confront reality as it is, not as we hoped it would be. It encourages humility, creativity, and openness. It reminds us that understanding the universe is not about imposing order, but about discovering how order and chaos coexist. James Webb has not revealed a flaw in nature, it has revealed a flaw in our expectations. And by doing so, it has brought us one step closer to a universe that is not simplified for our understanding, but understood on its own terms. As the discussion deepens, another realization begins to emerge, one that quietly reshapes how scientists think about discovery itself. The planet revealed by James Webb is not simply challenging existing models, it is changing the relationship between observation and explanation. For a long time, astronomers believed that if enough data were collected, the universe would eventually reveal a clean underlying logic. Webb is showing that data does not always simplify reality. Sometimes it does the opposite. This planet sits at the intersection of precision and ambiguity. On one hand, the measurements are extraordinarily precise. The atmospheric spectra are clear. The molecular signatures are strong. The uncertainties are smaller than ever before. And yet, the conclusions are less certain than those drawn from far noisier data in the past. This is an unfamiliar position for science to occupy. Usually, better data narrows interpretation. Here, it widens it. This widening is not due to error, but to richness. The planet's properties intersect multiple theoretical regimes at once. It behaves partially like one class of planet and partially like another, without fully belonging to either. In earlier eras, such ambiguity might have been dismissed as insufficient resolution. Now, with Webb's clarity, it must be taken seriously. This leads to a deeper epistemological question. What does it mean to understand a planet? For decades, understanding meant fitting an object into a category. If a planet could be labelled gas giant, terrestrial, ice giant, then its behaviour could be inferred. James Webb is undermining that comfort. It suggests the categories may be conveniences rather than truths. Planets may not exist to satisfy our classifications. They may exist along continuous spectra of properties shaped by unique histories. The planet that breaks formation models forces scientists to confront the limits of reductionism. Breaking a system into simpler parts works well when interactions are weak or linear. Planet formation, it now appears, may be neither. Interactions between disk chemistry, gravity, radiation, timing and migration can produce outcomes that cannot be predicted by isolating any single factor. This realization encourages a systems-level approach. Instead of modeling isolated processes, scientists are beginning to treat planetary systems as evolving networks of interactions. In such networks, feedback loops matter. Small changes can cascade. Delays can amplify effects. Outcomes emerge rather than being directly caused. James Webb's planet appears to be an emergent outcome. This perspective aligns planetary science more closely with fields like climate science, ecology, and complex systems theory. In those fields, prediction is often probabilistic rather than deterministic. Models aim to reproduce patterns and distributions, not exact events. Accepting this approach in planetary science represents a significant cultural shift. There is also a temporal dimension to this change. Most formation models implicitly assume that early events dominate planetary outcomes. Once formation is complete, evolution is treated as secondary. Webb's observations challenge that timeline. The planet's atmosphere suggests ongoing or repeated processes that blur the distinction between formation and evolution. This means that planets may never truly finish forming. Instead, they may continue to change in response to internal dynamics and external influences throughout their lifetimes. The concept of a finished planet may be a simplification imposed for convenience rather than a physical reality. This has consequences for how scientists interpret exoplanet populations. Statistical studies often treat planets as static points in parameter space. Webb's planet suggests that those points may represent snapshots of ongoing trajectories. Two planets with similar properties today may diverge significantly over time, while two that appear different may converge. Such dynamism complicates comparison but enriches understanding. It suggests that planetary diversity is not just a result of different starting conditions, but of different evolutionary pathways unfolding over billions of years. Another important implication concerns how scientific consensus forms. Consensus often emerges when multiple independent lines of evidence converge on a single explanation. Webb's planet resists convergence. Different datasets point in different directions. This does not mean consensus is impossible, but it may take a different form. Instead of agreeing on a single formation pathway, scientists may agree on a range of plausible histories. Consensus may shift from "this is how it formed" to "these are the ways it could have formed, and here is why we cannot narrow it further." This kind of consensus is less satisfying emotionally but more honest scientifically. There is also a broader lesson here about the pace of discovery. James Webb is delivering transformative data at a speed that challenges the community's ability to absorb it. Models take time to develop, interpretations take time to test. In the meantime, observations accumulate, sometimes outpacing explanation. This creates a temporary imbalance. Data-rich, theory-poor periods can feel uncomfortable, but they are often precursors to major breakthroughs. The history of science shows that such moments force new frameworks to emerge. The planet that breaks formation models may be one of the catalysts for such a framework in planetary science. It is also worth considering how this discovery reshapes public narratives about science. Popular portrayals often emphasize certainty and progress. Webb's planet highlights a different aspect: science as an ongoing process of questioning and revision. This narrative is less tidy but more faithful to reality. By confronting a planet that defies expectations, scientists demonstrate intellectual humility. They show that knowledge is provisional, that theories are tools rather than truths, and that surprise is not failure but fuel. This humility has value beyond astronomy. It models a way of thinking that is adaptable, resilient, and open to complexity. There is also an aesthetic dimension to this shift. A universe that produces planets with irreducible histories is more interesting than one that follows rigid templates. Diversity becomes a feature rather than a complication. Each world carries a story shaped by chance, interaction, and time. James Webb's planet invites us to see planetary systems not as products of assembly lines, but as outcomes of cosmic narratives, stories written by physics, but edited by circumstance. As more planets are observed with similar detail, scientists will likely discover that many do not fit neatly into existing categories. The initial discomfort will give way to familiarity. What feels strange now may become expected later. The boundaries of normal will expand. In that sense, the planet that breaks every formation model may eventually lose its status as an outlier. It may become representative of a broader truth, that planetary formation is not governed by a small set of universal rules, but by a complex interplay of conditions that produce endless variation. This realization does not weaken science, it strengthens it. It pushes theories to become more flexible, more inclusive, and more reflective of reality's complexity. James Webb has not made the universe harder to understand, it has made it more honest. By revealing a planet that resists simplification, it reminds us that understanding does not always mean reducing complexity. Sometimes it means learning how to live with it, map it, and appreciate it without forcing it into familiar shapes. The discovery marks a transition point. Planetary science is moving from an era of classification to an era of interpretation, from certainty to nuance, from expectation to exploration. And at the centre of that transition is a planet that quietly insists on being understood on its own terms, not ours. As attention continues to widen around this discovery, the conversation begins to drift into a more subtle but deeply important territory, the limits of narrative itself in science. For a long time, planetary science has relied on clear stories. A disk forms, material settles, planets grow, systems stabilize. These stories are not wrong, but they are selective. They highlight what is common and suppress what is inconvenient. The planet revealed by James Webb resists being placed into a clean narrative, and in doing so, it exposes how much of scientific understanding depends on storytelling choices rather than raw reality. Every scientific model is, at some level, a story about cause and effect. It explains how one state leads to another in a sequence that feels coherent. What this planet does is interrupt that coherence. It presents an object whose properties point in multiple directions at once, refusing to line up into a single timeline. This does not mean the planet lacks a history. It means its history cannot be reduced to a simple sequence without losing essential information. This realization forces scientists to confront a question that is rarely asked explicitly. When does simplification become distortion? In order to be useful, models must simplify. They must ignore some variables to focus on others. But James Webb's observations suggest that some of the variables being ignored may not be secondary at all. They may be central. Processes once treated as minor complications, turbulence, timing offsets, disk asymmetries, episodic accretion, may actually shape outcomes in decisive ways. The planet's atmospheric composition provides a striking example. The coexistence of chemical signatures associated with different thermal regimes implies that the planet did not experience a single, steady environment during its formation. Instead, it likely passed through multiple regimes, or experienced conditions that fluctuated dramatically over time. Traditional models smooth out these fluctuations, treating disks as averaged environments. Webb's data suggests that those averages may conceal the very processes that matter most. This raises a deeper methodological concern. Many formation models aim to reproduce the final properties of planets, but they do not track the full history of how those properties emerge. If formation is episodic and path-dependent, then final states alone may not contain enough information to reconstruct the past accurately. Two planets with similar present-day properties could have arrived there through entirely different routes. James Webb's planet appears to carry precisely this kind of ambiguity. Its present state does not uniquely encode its past. Instead, it admits multiple plausible histories, each consistent with some aspects of the data and inconsistent with others. This is deeply uncomfortable for a field that has long sought unique explanations, yet this discomfort may be productive. In other areas of science, ambiguity is accepted as a natural feature of complex systems. In evolutionary biology, for example, multiple evolutionary paths can lead to similar traits. In geology, different processes can produce similar landforms. The goal is not always to identify a single history, but to constrain the space of possibilities. Planetary science may be moving toward a similar stance. James Webb's discovery suggests that the field must learn to live with underdetermination, where data constrains but does not fully determine interpretation. This does not weaken conclusions, it changes their nature. Another implication of this shift concerns prediction. If planet formation outcomes depend sensitively on chaotic and historical factors, then predicting specific planets becomes less feasible. Instead, prediction must operate at the level of populations. Scientists may be able to say how common certain types of planets are, but not exactly where or how individual ones form. This perspective aligns well with the statistical nature of much of modern astrophysics. Large surveys already emphasize trends over specifics. Webb's detailed observations complement this by showing how much variation exists within those trends. The planet that breaks formation models thus sits at an intersection between two modes of science, detailed case study and broad statistical analysis. It demonstrates the power of focusing deeply on a single object, while also revealing the limitations of generalization. There is also an important lesson here about technological progress. James Webb did not create this complexity. It revealed it. The planet existed before Webb observed it. Its strange properties were always there. What changed is our ability to see them. This suggests that future instruments may reveal even deeper layers of complexity. As observational capabilities improve, models will continue to be challenged. Each new level of resolution may uncover processes that were previously invisible and therefore unaccounted for. This is not a sign that science is failing. It is a sign that it is working as intended. Another dimension of this discovery is its impact on how scientists think about anomalies. In the past, anomalies were often treated as temporary irritations, expected to disappear with better data or improved models. James Webb's planet suggests that some anomalies are not errors to be corrected, but signals to be interpreted. This requires a change in attitude. Instead of trying to force observations into existing frameworks, scientists must be willing to let frameworks bend or even break. This takes intellectual courage, especially in a field where careers and reputations are built on established theories. Yet history shows that such courage is rewarded. Many of the most significant advances in science came from taking anomalies seriously, rather than dismissing them. The orbit of Uranus led to the discovery of Neptune. The precession of Mercury's orbit led to general relativity. Cosmic microwave background fluctuations reshaped cosmology. James Webb's planet may play a similar role for planetary science. There is also a cultural implication for how science is taught and communicated. Textbooks often present formation models as settled knowledge, with clear diagrams and tidy explanations. Webb's discovery suggests that such presentations may need revision. Planet formation is not a solved problem. It is an evolving field, and students should be introduced to its uncertainties as well as its successes. This transparency has value. It shows science as a living process rather than a static body of facts. It prepares future researchers to think flexibly and creatively rather than rigidly. Another subtle consequence concerns the language scientists use. Words like should, must, and cannot appear frequently in discussions of formation models. James Webb's planet undermines the confidence implied by those words. It reminds us that physical law allows a wider range of outcomes than our simplified expectations capture. The planet does not violate physics, it violates convenience. This distinction is crucial. Nature is under no obligation to behave in ways that are easy to model or explain. Physics sets constraints, but within those constraints, reality may explore vast and surprising possibilities. James Webb's discovery encourages scientists to focus more on constraints than on prescriptions. Instead of declaring what planets must do, they can identify what planets cannot do and explore the space in between. This approach is more humble and more resilient. It allows new discoveries to be integrated rather than resisted. As this mindset spreads, planetary science may undergo a quiet transformation. The emphasis may shift from constructing universal narratives to mapping landscapes of possibility. Models may become less rigid but more inclusive. Explanations may become less definitive but more honest. The planet that breaks formation models thus serves as a catalyst for intellectual evolution. It pushes the field toward a more mature understanding of complexity, uncertainty, and diversity. Ultimately, this discovery reminds us that the universe is not a machine that produces identical outcomes from identical inputs. It is a dynamic system where history matters, chance matters, and interactions matters. Worlds emerge not just from rules but from context. James Webb has given us a glimpse into that reality. It has shown us a planet that refuses to be simplified, and in doing so, it challenges us to expand not just our models, but our expectations. The real breakthrough here is not about one planet. It is about learning how to think differently about all of them. And that shift, quiet and gradual though it may be, could reshape planetary science for decades to come. As the discussion stretches further, the focus naturally turns toward how this discovery reshapes the future of planetary science itself, not just in theory, but in practice. James Webb has not only revealed a planet that resists explanation, it has exposed how deeply our investigative tools, methods, and expectations are intertwined. The planet becomes a mirror, reflecting the structure of scientific inquiry as much as the structure of the cosmos. One of the most significant shifts prompted by this discovery is how scientists define success in explanation. Traditionally, success meant convergence. Multiple lines of evidence leading toward a single stable conclusion, but with this planet, convergence refuses to happen. Instead, evidence fans outward, pointing to several overlapping possibilities. This forces a re-evaluation of what it means to solve a scientific problem. Perhaps some problems are not solved by narrowing answers, but by mapping them. This planet's existence suggests that planetary formation is not a question with a single correct answer, but a question space, a region of possibilities bounded by physical law yet filled with variation shaped by timing, environment, and interaction. James Webb is not pointing to a missing equation, it is pointing to a missing mindset. This shift is already influencing how future observations are prioritized. Instead of focusing primarily on planets that fit well into existing categories, astronomers are increasingly drawn to those that don't. The unusual becomes valuable not because it is rare, but because it reveals where theory is incomplete. James Webb's ability to characterize atmospheres makes it uniquely suited to this role, transforming it from a confirmatory instrument into an exploratory one. This has practical consequences. Observation proposals now emphasize diversity rather than representativeness. Scientists want to observe planets at extremes, planets in unexpected locations, planets with unusual temperatures or chemical signatures. The goal is no longer to reinforce known patterns, but to stress test them. In this sense, the planet that breaks formation models becomes a prototype for a new observational strategy. It shows that the most informative discoveries may lie at the edges of expectation rather than at the center. There is also a computational consequence. Modeling such complexity requires a new generation of simulations. Instead of single-run models optimized to produce tidy results, scientists are developing ensembles of simulations that explore wide ranges of initial conditions. These simulations are not designed to predict one outcome, but to reveal families of outcomes. This approach borrows from fields like climate modeling, where uncertainty is embraced rather than eliminated. Climate scientists do not predict a single future climate, they predict ranges of possible futures under different conditions. Planetary science is beginning to move in a similar direction. James Webb's planet fits naturally into this framework. It is not an outlier to be explained away, but a data point that expands the distribution. It forces models to become broader, more flexible, and more honest about uncertainty. Another important implication concerns how scientists interpret null results. When models fail to reproduce an observation, the failure itself becomes informative. It highlights which assumptions are too restrictive and which variables may be missing. The planet's resistance to explanation acts as a diagnostic tool, revealing weaknesses in theoretical frameworks. This diagnostic role is subtle but powerful. It allows science to improve not by confirmation, but by friction. There is also a temporal implication for how scientific understanding evolves. Large discoveries often arrive in phases. First comes surprise, then confusion, then debate, then, gradually, integration. James Webb's planet appears to be in the early stages of this cycle. The debates are active. Interpretations are provisional. Integration has not yet occurred. This period of uncertainty can feel unsettling, but it is also when creativity flourishes. New ideas are proposed, old assumptions are questioned, and interdisciplinary approaches gain traction. The field becomes intellectually alive in ways that are not always visible during periods of consensus. The planet's discovery also influences how planetary science relates to broader cosmology. Planet formation does not occur in isolation. It is shaped by stellar evolution, galactic environment, and cosmic chemical history. James Webb's observations hint that these larger contexts may matter more than previously thought. For example, the chemical makeup of a protoplanetary disk depends on the history of star formation and supernova enrichment in its region of the galaxy. A planet forming in one part of the Milky Way may have access to different materials than one forming elsewhere. This adds another layer of diversity that formation models must account for. The planet that breaks formation models may thus reflect not just local conditions but galactic history. Its unusual composition could be a consequence of where and when its star formed within the broader cosmic timeline. This idea connects planetary science to questions about the chemical evolution of galaxies. It suggests that understanding planets requires understanding stars, galaxies, and even cosmology. James Webb, with its ability to observe across vast distances and timescales, is uniquely positioned to bridge these domains. There is also a subtle human dimension to this discovery. Science is often portrayed as detached and objective, but it is carried out by people with expectations, intuitions, and cognitive biases. The surprise generated by this planet reveals how deeply those expectations shape interpretation. When models work well, they become invisible. When they fail, they become obvious. James Webb's planet has made visible the scaffolding of planetary science, showing where assumptions were quietly guiding thought. Recognizing those assumptions is a step toward more reflective and resilient science. This reflection extends to education and communication. How should such discoveries be explained to the public? The temptation is to frame them as dramatic contradictions or sensational anomalies, but the deeper story is about process rather than shock. It is about how knowledge grows through challenge and revision. James Webb's planet offers an opportunity to communicate science as an evolving dialogue with nature, rather than a collection of finished answers. This narrative may be less immediately satisfying, but it is more accurate and more inspiring in the long run. There is also an ethical dimension to how such discoveries are framed. Overstating certainty risks misleading audiences. Understating complexity risks diminishing the significance of the discovery. Finding the balance requires care. The planet does not break physics. It reveals that our representations of physics are incomplete. That distinction matters. As research continues, it is likely that new data will refine interpretations. Some aspects of the planet may become clearer, others may remain ambiguous. This is not a flaw, it is a reflection of the limits imposed by time, distance, and complexity. What will likely persist is the shift in perspective this discovery has initiated. Planetary science will not return to a simpler worldview. Once complexity is seen, it cannot be unseen. James Webb has opened a door that does not close easily. The planet that breaks formation models is not important because it is strange. It is important because it forces scientists to reconsider how they know what they know. It challenges the field to move beyond comfort, beyond tidy narratives, and toward a deeper engagement with reality's intricacy. In the end, this discovery may be remembered not for the details of one planet's atmosphere or orbit, but for how it changed the questions scientists asked afterward. Instead of asking how closely reality matches theory, they may increasingly ask how theory must adapt to accommodate reality. That shift, quiet and gradual, may be James Webb's most enduring contribution. Not answers, but better questions. And in science, that is often where true progress begins. As the conversation moves even further outward, another consequence of this discovery begins to take shape. One that is less about planets and more about how scientific confidence itself is constructed. The planet observed by James Webb does not simply disrupt a technical framework, it exposes how much certainty in science depends on repetition. When patterns repeat often enough, they begin to feel inevitable. When something breaks that repetition, it reveals how fragile inevitability really is. For years, the growing catalogue of exoplanets appeared to confirm that planetary systems follow a limited number of architectural styles. Variations existed, but they seemed to cluster around familiar themes. This repetition reinforced the belief that the dominant formation mechanisms were not only correct, but sufficient. James Webb's planet interrupts that reinforcement. It demonstrates that repetition does not guarantee completeness. It may simply reflect what we were capable of observing at the time. This realization encourages a more cautious interpretation of large datasets. Thousands of planets can still represent a biased sample if the observational window is narrow. Webb's ability to probe atmospheres in detail reveals dimensions of planetary diversity that were previously compressed or invisible. It shows that even a large number of observations can hide structural blind spots. The planet's existence also challenges the idea that scientific understanding advances linearly. It is tempting to imagine knowledge as a steady accumulation of facts, each discovery filling a gap. In reality, progress often arrives through disruption. New tools do not simply add information, they change what information matters. James Webb has altered the hierarchy of evidence. Atmospheric chemistry now carries more weight than orbital position alone. Internal processes now rival formation location in importance. Time and sequence now compete with distance and mass as explanatory variables. The planet that breaks formation models embodies this reordering of priorities. This reordering affects how theories are evaluated. A theory that once seemed robust may now appear narrow. A theory that once seemed speculative may now appear prescient. The planet acts as a stress test, revealing which ideas are flexible enough to survive contact with richer data. There is also an important lesson here about restraint. In the early days following the discovery, there is a temptation to rush toward explanation, to claim that the mystery has been solved or that a new paradigm has arrived. James Webb's data discourages such haste. The planet's complexity resists premature closure. It invites patience. This patience is not passive. It involves careful reanalysis, alternative modelling approaches, and deliberate skepticism towards simple narratives. It requires scientists to sit with uncertainty rather than eliminate it too quickly. This posture is intellectually demanding, but it is also deeply scientific. Another dimension of this discovery concerns how science handles contradiction. Contradiction is often framed as a sign of error, but in complex systems, contradiction may signal that multiple processes are operating simultaneously. The planet's properties contradict each other only if one assumes that a single process must dominate. If multiple processes overlap, contradiction dissolves into coexistence. James Webb's planet may be a product of coexistence rather than conflict. Cold chemistry and warm chemistry may not be mutually exclusive if the planet experienced different environments at different times. Migration and in situ formation may not be alternatives if the planet's history includes both. Stability and chaos may not be opposites if stability emerges from chaotic interactions. This perspective requires a more nuanced vocabulary. Instead of asking which model is correct, scientists may ask which combination of models best accounts for the data. Explanation becomes additive rather than exclusive. This has implications for how scientific debates unfold. Debates often frame positions as competing alternatives. James Webb's planet suggests that such framing may be misleading. The truth may lie not in choosing one explanation over another, but in understanding how multiple explanations intersect. There is also a practical implication for how research is funded and organized. Complex explanations require collaboration across subfields. They require longer-term projects that do not promise quick resolution. They require tolerance for ambiguity in grant proposals and publications. James Webb's discovery may encourage institutions to value exploratory research more explicitly. Another subtle consequence concerns how uncertainty is communicated. Scientists are trained to quantify uncertainty, but not always to narrate it. Webb's planet demands narrative uncertainty, a willingness to say not just "we don't know," but "we may never know this aspect definitively." This kind of honesty can be uncomfortable, but it builds trust. The planet also reframes the relationship between expectation and discovery. Many scientific instruments are designed with specific questions in mind. James Webb was built in part to study atmospheres and search for habitable worlds. Discovering a planet that disrupts formation theory was not its primary mission, but it may become one of its most influential contributions. This highlights an important truth. The most transformative discoveries are often unintended. They arise not from asking the right questions, but from being prepared to listen when nature answers a different one. There is also a long-term implication for how future missions are conceived. Webb's success in revealing complexity may encourage designers to prioritize versatility over specialization. Instruments that can adapt to unexpected findings may prove more valuable than those optimized for narrow goals. The planet that breaks formation models thus influences not only current theory but future exploration. On a deeper level, this discovery invites reflection on why humans seek patterns in the first place. Patterns provide comfort. They make the universe feel navigable. James Webb's planet does not eliminate patterns, but it reminds us that patterns are approximations, not guarantees. Nature appears to favor variation within constraint. Physical laws set boundaries, but within those boundaries, outcomes can be wildly diverse. This diversity is not noise, it is expression. Accepting this view does not make science less predictive. It makes it more realistic. Predictions become probabilistic rather than absolute. Expectations become flexible rather than rigid. The planet observed by James Webb is a reminder that the universe is not obligated to behave in ways that confirm our intuitions. It operates according to laws that permit complexity, contingency, and surprise. Our task is not to force simplicity onto that reality, but to develop tools and concepts that can accommodate it. As planetary science continues to evolve, this discovery may come to be seen as a pivot point, a moment when the field moved from seeking universal scripts to mapping diverse narratives. From expecting planets to behave to listening to what they reveal, James Webb has not closed a chapter in planetary science. It has opened one that is more challenging, more nuanced, and ultimately more honest. The planet that breaks formation models stands as a quiet reminder that understanding the universe is not about reducing it to what we expect, but about expanding our expectations to meet it where it truly is. As this discovery continues to echo through the scientific community, a more reflective realization begins to take hold. The planet revealed by James Webb is not only changing what scientists think about planet formation, but how they think about knowledge itself. It exposes a subtle tension between explanation and acceptance, between the desire to resolve uncertainty and the recognition that some uncertainty may be inherent. For much of scientific history, progress has been associated with reduction. Complex phenomena are broken down into simpler components until a clear mechanism emerges. This approach has been extraordinarily successful in many domains, but the planet that breaks formation models suggests that reduction alone may not be sufficient when dealing with systems shaped by long chains of interaction, feedback, and contingency. Planet formation may not be reducible to a single dominant mechanism because no such mechanism exists in isolation. Instead, formation may be an emergent outcome of many interacting processes, none of which fully determine the result on their own. In such systems, understanding does not come from isolating causes, but from tracing relationships. James Webb's observations push planetary science toward this relational view. The planet's properties do not point cleanly back to one cause. They point outward toward networks of influence. Disk chemistry interacting with stellar radiation, timing interacting with migration, internal heating interacting with atmospheric retention. Each factor contributes, but none dictates. This realization reshapes how scientists interpret causality. Instead of asking, what caused this planet to form this way, they may increasingly ask, What conditions made this outcome possible? That shift changes explanation from a single answer to a structured landscape of contributing factors. This approach aligns with how complex systems are studied elsewhere. In neuroscience, behavior emerges from networks rather than single neurons. In ecology, ecosystems are shaped by interactions rather than dominant species. In climate science, global patterns arise from countless coupled processes. Planetary science, it now appears, belongs in this family of disciplines. There is also an epistemic humility embedded in this shift. It acknowledges that some aspects of planetary history may be fundamentally underdetermined. Even with perfect data, certain details may remain ambiguous because different histories can produce similar outcomes. This is not a failure of measurement, but a feature of complexity. James Webb's planet highlights this underdetermination clearly. Its atmosphere allows multiple formation narratives to coexist. Choosing between them may not be possible without additional assumptions. Recognizing this limitation is a mark of maturity in a scientific field. Another implication of this discovery is how it reframes the role of surprise in science. Surprise is often treated as a temporary state, a signal that something is wrong and must be fixed. But surprise can also be a permanent companion when exploring unfamiliar domains. James Webb is venturing into parameter spaces that were previously inaccessible. In such spaces, surprise should be expected rather than avoided. This perspective changes how scientists emotionally relate to their work. Instead of seeking closure, they learn to value openness. Instead of aiming for final answers, they aim for deeper questions. The planet that breaks formation models becomes not a puzzle to be solved quickly, but a teacher revealing the limits of certainty. There is also a generational aspect to this transition. Younger scientists entering the field may grow up with James Webb's data as their baseline. For them, complexity and ambiguity will not feel like disruptions, they will feel normal. This may shape a generation of researchers more comfortable with probabilistic thinking and less attached to rigid frameworks. Such a shift can have lasting effects. It influences how hypotheses are framed, how models are built, and how results are communicated. It encourages intellectual flexibility and resilience. Another layer of consequence emerges when considering how planetary science intersects with philosophy. Questions about formation, causality, and explanation are not purely technical. They touch on deeper issues about what it means to explain something at all. Is an explanation required to be unique? Is it required to be predictive? Or is it sufficient that it constrains possibilities and reveals structure? James Webb's planet pushes toward the latter view. Explanation becomes about understanding constraints, rather than identifying a single origin story. This approach is less satisfying narratively, but more faithful to the complexity of the universe. There is also a cautionary lesson embedded in this discovery about overconfidence. For decades, planetary science progressed rapidly, fueled by new detections and improving models. That progress can create an illusion of completeness. Webb's planet punctures that illusion gently but decisively. It reminds us that even well-supported frameworks can be provisional. This does not diminish past achievements, it contextualizes them. Models were never wrong, they were incomplete. Webb reveals what lies beyond their boundaries. Another subtle effect of this discovery is its influence on interdisciplinary boundaries. Understanding this planet requires collaboration between observers, theorists, chemists, and computational scientists. It blurs traditional divisions between subfields. Atmospheric chemistry becomes inseparable from formation theory. Stellar physics becomes inseparable from planetary evolution. This convergence may shape the future structure of planetary science as a discipline. Training programs may become more integrative, research groups may become more interdisciplinary. The planet that breaks formation models thus acts as a catalyst not only for theoretical change, but for institutional change. There is also a narrative implication for how humanity relates to the cosmos. Discoveries that challenge expectations can feel destabilizing, but they can also be enriching. They remind us that the universe is not a solved problem, but an ongoing conversation. Each new observation adds a new voice. James Webb's planet speaks softly but insistently. It does not shout its mystery. It simply exists, carrying properties that refuse to align neatly with our stories. In doing so, it invites patience, curiosity, and humility. As the field continues to evolve, it is likely that this planet will be joined by others that challenge formation models in different ways. Some may contradict assumptions about mass. Others may challenge ideas about composition or timing. Together, they will form a mosaic of diversity that reshapes the field's conceptual foundations. Looking back, scientists may see this moment as the beginning of a transition, from a phase focused on discovering planets to a phase focused on understanding planetary diversity. James Webb's role in this transition is central, but not because it provides answers, because it provides perspective. The planet that breaks formation models teaches a simple but profound lesson. Reality does not organize itself to match our expectations. Our task is not to force alignment, but to listen carefully and adjust our understanding accordingly. In that sense, this discovery is not unsettling. It is reassuring. It shows that science remains responsive to evidence, capable of revision, and open to complexity. It demonstrates that knowledge is not a static monument, but a living structure that grows by absorbing contradiction. James Webb has not revealed a universe that is chaotic in the sense of being lawless. It has revealed a universe that is rich, layered, and deeply contextual. A universe where outcomes are shaped by histories we may only partially recover. And in doing so, it reminds us why exploration matters, not because it confirms what we already believe, but because it expands the space of what we are willing to imagine. As the conversation continues to unfold, the significance of this discovery begins to extend beyond science and into how humans mentally frame uncertainty, expectation, and meaning. The planet revealed by James Webb does something subtle but profound. It undermines the quiet assumption that understanding must eventually converge towards simplicity. Instead, it suggests that understanding may deepen by accepting complexity as an endpoint rather than a temporary obstacle. For much of scientific history, complexity has been treated as a phase to be passed through. Early models are crude, reality is messy, but with enough refinement, the mess resolves into elegant laws. This approach has worked remarkably well in many domains. But planetary formation, as James Webb is revealing, may not obey that trajectory. Complexity may not collapse into elegance. It may persist. The planet's resistance to simplification suggests that there may be no final clean description of how worlds form, only increasingly rich descriptions that capture more of the variability nature allows. This is not a pessimistic conclusion. It is an honest one. It acknowledges that some systems are intrinsically complex, not because we lack intelligence, but because reality itself is layered. This realization reshapes how scientists think about explanatory depth. Depth no longer means drilling down to a single mechanism. It means understanding how many mechanisms interact, overlap, and sometimes interfere with one another. James Webb's planet demands this kind of depth. Any explanation that focuses too narrowly immediately fails. There is also an important shift in how uncertainty is valued. In earlier eras, uncertainty was often treated as a weakness, something to be minimized or eliminated. Now, uncertainty becomes informative. It reveals where models are flexible and where they are brittle. The planet's ambiguity highlights precisely those regions where understanding must grow. In this sense, uncertainty becomes a guide rather than a flaw. Another consequence of this discovery is how it influences scientific patience. Planetary formation unfolds over millions of years, yet observations are snapshots taken over hours or days. Bridging that gap requires restraint in interpretation. James Webb's planet reminds scientists that some answers may only emerge through accumulation over time, through repeated observation, comparison, and synthesis. This patience contrasts with the pace of modern information flow. Discoveries are shared instantly, debated publicly, and often pressured toward immediate conclusions. Webb's planet resists that pressure. It does not yield to quick interpretation. It requires slow thinking. This slow thinking aligns naturally with the kind of science James Webb enables. Its observations are detailed, subtle, and layered. They reward careful analysis rather than rapid generalization. In that sense, the planet is not just a subject of study, but a training ground for a different mode of inquiry. There is also a broader implication for how science relates to prediction. Much of modern science is judged by its predictive power, but in systems governed by sensitivity and contingency, prediction may be limited to ranges rather than specifics. James Webb's Planet suggests that planetary science may need to embrace this limitation openly. This does not mean abandoning prediction entirely, it means redefining its scope. Instead of predicting exact planetary configurations, scientists may aim to predict statistical distributions, likelihoods, and trends. They may focus on what is possible and probable rather than what is inevitable. This shift mirrors developments in other fields dealing with complex systems. In economics, ecology, and epidemiology, prediction is probabilistic, not deterministic. Planetary science may be joining this family of disciplines more fully than before. Another subtle effect of this discovery is how it reshapes scientific storytelling. Humans are natural storytellers. We seek narratives with beginnings, middles, and ends. Planet formation models often reflect this tendency. A planet forms, migrates, stabilizes. The story concludes. 161. James Webb's Planet disrupts this narrative structure. Its story does not have a clear beginning or end. It appears to be an ongoing process, shaped by multiple chapters that overlap and blur. This challenges scientists to tell different kinds of stories that acknowledge branching paths, unresolved questions, and open endings. Such storytelling may feel less satisfying, but it is more faithful to reality. It also invites deeper engagement. Instead of consuming a finished story, audiences are invited into a process of exploration. There is also an ethical dimension to how such discoveries are communicated. Overstating certainty can mislead. Oversimplifying complexity can create false confidence. James Webb's Planet encourages a more careful approach, one that respects the audience's ability to engage with nuance. This approach aligns with a broader cultural shift toward valuing transparency and humility in expertise. Acknowledging what is not known does not weaken authority. It strengthens trust. Another implication concerns how planetary science defines progress. Progress may no longer be measured by how well models converge on a single explanation, but by how effectively they accommodate diversity without contradiction. A good model may be one that remains useful even when confronted with unexpected outcomes. James Webb's Planet serves as a benchmark for such robustness. Models that cannot accommodate it without breaking may need revision. Models that can adapt may point the way forward. This adaptability has practical consequences for future research. It encourages modular models that can incorporate new processes without being rebuilt entirely. It encourages openness to revision rather than defensive preservation of established frameworks. There is also a long-term implication for how humanity understands its cosmic environment. If planetary systems are shaped by contingent histories rather than universal scripts, then Earth's history becomes one among many, not a template. This perspective is both humbling and enriching. It situates humanity within a vast landscape of possibility, rather than at the centre of a predetermined design. James Webb's Planet reinforces this view. It shows that worlds can exist in forms we did not anticipate, shaped by paths we did not imagine. It suggests that the universe is more creative than our theories allow. This creativity does not violate physical law. It operates within it. Physics sets boundaries, but within those boundaries, outcomes can be endlessly varied. The planet that breaks formation models exists comfortably within physical law, yet outside our expectations. This distinction is crucial. It reminds us that physical law is permissive, not prescriptive. It defines what cannot happen, not what must happen. As this realization settles, planetary science may begin to adopt a more exploratory posture. Instead of seeking to confirm expectations, scientists may increasingly seek to discover what lies beyond them. Webb's Planet becomes not an anomaly but a compass pointing toward unexplored conceptual territory. In this sense, the discovery does not close a chapter. It opens a frontier defined not by distance but by complexity. James Webb has shown that the universe does not simplify itself for our understanding. It invites us to meet it where it is, with patience, curiosity, and humility. The planet that breaks formation model stands as a quiet testament to that invitation. It does not demand an answer, it demands attention. And by demanding attention, it reshapes not only planetary science, but the way we approach knowledge itself, slowly, carefully, and with respect for the richness of reality. As this exploration continues, the discovery begins to feel less like a disruption and more like a quiet recalibration of perspective. The planet revealed by James Webb does not announce a new rule. It reveals how much our understanding depended on the comfort of familiar boundaries. What once felt like firm edges now appear soft, provisional, and shaped by the limits of what we could observe. One of the most subtle shifts introduced by this discovery is how scientists think about explanation versus description. For many years, explanation meant tracing a clear line from cause to outcome. A planet formed here, from this material, at this time, following this pathway. James Webb's planet resists that clarity. Instead, it invites a richer description, one that may never collapse into a single explanatory thread. This does not mean explanation has failed, it means explanation may need to evolve. Rather than asking how this planet formed, scientists increasingly ask what range of conditions could plausibly produce something like it. The emphasis shifts from reconstructing a unique past to understanding a landscape of possibility. This approach does not deny history. It acknowledges that some histories overlap so completely that they leave indistinguishable traces. This is a difficult idea to accept because it challenges a deeply held intuition that with enough data, every past can be reconstructed. In simple systems, this is often true. In complex systems, it is not. Planet formation, as James Webb is revealing, belongs to the latter category. The planet's atmosphere exemplifies this complexity. Its chemical composition does not point backward to a single moment of origin. Instead, it appears layered, as if shaped by multiple epochs, early disk conditions, later stellar influence, internal evolution, perhaps even episodic replenishment. Each layer tells part of the story, but no single layer tells the whole. This layered nature of evidence changes how certainty is distributed. Confidence no longer rests in a single interpretation, but in the recognition that several interpretations remain viable. This is not ambiguity born of ignorance, but ambiguity born of richness. There is a parallel here with how geologists interpret Earth's history. Rocks record events, but erosion, mixing, and metamorphism blur those records. Geologists do not expect to recover every detail. They work with partial histories, constrained by physical principles but open to multiple narratives. Planetary science may be moving toward a similar mindset. James Webb's planet pushes the field in that direction. Another consequence of this discovery is how it reshapes the role of expectation in scientific reasoning. Expectations are necessary. They guide observation and interpretation, but when expectations become invisible, they can quietly limit imagination. The planet that breaks formation models makes those expectations visible again. It reveals how much confidence was placed in the idea that formation pathways are few and repeatable. That confidence was reasonable, given the data available at the time. But Webb's data suggests that repeatability may coexist with divergence, that similar beginnings can yield very different outcomes depending on timing, interaction, and chance. This realization has implications for how anomalies are treated going forward. Instead of asking whether an anomaly fits into existing theory, scientists may ask what the anomaly reveals about the theory's boundaries. The goal shifts from assimilation to illumination. There is also a shift in how evidence is weighted. Previously, orbital properties often carried more interpretive power than atmospheric chemistry. James Webb reverses that hierarchy. Chemistry becomes central. It carries memory. It preserves traces of environments long gone. This shift may redefine how future discoveries are prioritized. Worlds with accessible atmospheres may be more informative than those with well-defined orbits alone. The story of a planet may be written more clearly in what it contains than in where it resides. Another layer of consequence involves the relationship between observation and imagination. Science often advances by imagining possibilities and then testing them. James Webb's planet challenges imagination itself. It reveals possibilities that were not imagined at all. This is a humbling moment. It reminds us that imagination is constrained by experience. When experience expands, imagination must follow. The universe does not wait for us to imagine what it is capable of producing. This humility is not discouraging, it is liberating. It frees scientists from the expectation that understanding must always feel complete. It allows inquiry to remain open-ended. There is also a temporal humility embedded in this discovery. Planet formation unfolds over millions of years, but our observational window is brief. James Webb provides snapshots, not movies. The planet we see today is a moment in a much longer story. Some chapters may be inaccessible, not because they are hidden, but because they are erased by time. Accepting this limitation does not weaken science. It clarifies its scope. It defines what can be known and what must remain inferred. Another subtle implication concerns how progress is measured. Progress may no longer be judged by how closely models converge, but by how effectively they accommodate diversity. A successful model may be one that survives contradiction rather than eliminates it. This redefinition of success aligns planetary science with other mature disciplines that study complex systems. In such fields, models are valued for resilience, not precision alone. James Webb's planet becomes a benchmark for resilience. Any theory that cannot incorporate it without collapse reveals its fragility. Any theory that adapts reveals strength. There is also a shift in how scientific narratives end. Traditional narratives move toward closure. They explain, resolve, conclude. The narrative emerging around this planet moves toward openness. It ends not with resolution, but with expansion. This may feel unsatisfying to audiences accustomed to answers, but it is a more faithful reflection of how knowledge grows. Understanding often expands by recognizing what cannot yet be resolved. The planet that breaks formation models thus becomes a symbol, not of failure, but of transition. It marks a moment when planetary science steps into a phase of greater maturity where complexity is not a problem to be solved quickly, but a reality to be engaged patiently. As more data arrives, some aspects of this planet's story will sharpen. Others may blur further. Both outcomes are valuable. Sharpness reveals structure, blur reveals depth. In the long arc of scientific history, discoveries like this are often remembered less for their details than for how they change thinking. They shift assumptions, recalibrate expectations, and quietly redirect inquiry. James Webb's planet may one day be seen in this light, not as the planet that confused scientists, but as the planet that taught them how to ask better questions. It reminds us that the universe is not obligated to be simple, consistent, or convenient. It is obligated only to obey its laws, and within those laws it may explore possibilities far beyond what we anticipate. In that realization there is a kind of calm, the calm of knowing that uncertainty is not an enemy but a companion. That understanding does not end but deepens. And that exploration, when approached slowly and honestly, remains one of the most meaningful human endeavours. The planet does not demand an explanation, it invites attention, patience, and a willingness to let understanding evolve, quietly over time, just as the universe itself does. As this journey reaches its later stages, the discovery begins to take on a quieter, more reflective character. The urgency to explain gives way to something slower and more contemplative. The planet revealed by James Webb is no longer just a challenge to models. It becomes a lens through which scientists reconsider what it means to know something in a universe that is both lawful and endlessly variable. At this point, it becomes clear that the discomfort surrounding this planet does not come from ignorance, but from confrontation. Confrontation with the idea that nature may not organize itself into the kinds of categories that human reasoning finds most comfortable. For a long time, classification felt like progress. Once a planet could be placed into a group, its behavior seemed understandable by association. This planet resists that logic. It occupies a space between categories, borrowing features from several without committing fully to any. This resistance forces a re-evaluation of classification itself. Categories are tools, not truths. They help organize knowledge, but they can also obscure nuance. James Webb's observations reveal nuance at a level that makes rigid categorization feel inadequate. The planet is not misclassified, it is under-described. This realization subtly shifts the goal of planetary science. Instead of forcing planets into predefined boxes, the field begins to ask how those boxes should be reshaped, or whether they should exist at all. Perhaps planetary diversity is better represented as continua rather than discrete types. Perhaps boundaries are gradients, not lines. The planet's atmosphere once again becomes central to this shift. Its chemical makeup does not correspond cleanly to any single formation environment. Instead, it appears to reflect a history of transitions. Cold processes leave traces alongside warm ones. Stable conditions coexist with signs of disruption. The atmosphere reads less like a birth certificate and more like a long, annotated manuscript. This manuscript cannot be summarized without losing meaning. Such complexity has consequences for interpretation. It means that certainty must be distributed differently. Instead of high confidence in a single explanation, there is moderate confidence in multiple constraints. Scientists can say what likely did not happen, what could have happened, and what remains unclear. This form of knowledge is less definitive but more robust. It also demands a different kind of patience from both researchers and audiences. The desire for a clean answer is natural, but the universe is not obligated to provide one. James Webb's planet teaches that understanding may require living with unresolved questions for extended periods, perhaps indefinitely. There is an emotional aspect to this patience. Scientists invest time, creativity, and identity into their models. When those models are challenged, it can feel personal. But science advances not by protecting frameworks, but by allowing them to be tested honestly. The planet's refusal to conform becomes an act of clarification rather than defiance. Another implication of this discovery is how it reframes the relationship between simplicity and truth. Simpler explanations are often preferred because they are easier to communicate and test. But simplicity is not always a property of reality. Sometimes it is a property of perspective. When perspective widens, simplicity dissolves into structure. James Webb widens perspective dramatically. It reveals details that were previously averaged away. Those details do not simplify the picture, they enrich it. The planet becomes more understandable in one sense. Its properties are measured with precision, but less predictable in another. This tension between measurement and prediction is characteristic of complex systems. Knowing more does not always mean predicting more. It often means understanding why prediction is limited. Another subtle shift emerges in how scientists think about error. Traditionally, error is associated with measurement uncertainty or flawed assumptions. James Webb's planet suggests another category, conceptual error. The idea that formation must follow a small set of dominant pathways may itself be the error, not because it is wrong in all cases, but because it is too narrow. Recognizing this kind of error is challenging because it requires stepping outside the framework in which success was previously defined. It requires asking whether the questions being asked are the right ones. This planet invites that kind of questioning. There is also a broader temporal implication. Scientific theories evolve slowly, often lagging behind observation. Webb's discovery accelerates this lag. It compresses decades of expected theoretical tension into a short period. The field must adapt quickly or risk clinging to outdated intuitions. This acceleration can feel destabilizing, but it is also energizing. It creates space for new ideas, new collaborations, and new ways of thinking. Periods of rapid conceptual change are often the most creative. The planet's influence also extends beyond planetary science. It touches on broader questions about how humans understand natural systems. It reinforces the idea that complexity is not an exception to be explained away, but a fundamental feature of many phenomena. From ecosystems to economies, from brains to climates, complexity resists reduction without becoming meaningless. Planet formation now joins this family of complex phenomena. There is also a quiet lesson here about expectation management. For years, each new exoplanet discovery seemed to bring us closer to a comprehensive theory. Webb's planet suggests that completeness may be an illusion. The universe may not offer a final theory of planet formation in the way we imagine. It may offer only increasingly refined approximations. This does not make the effort futile, it makes it human. Another consequence of this realization is how it shapes the long-term goals of observation. Instead of seeking confirmation, scientists may increasingly seek contradiction, not for its own sake, but because contradiction reveals where understanding is incomplete. James Webb's greatest contribution may be its ability to expose those gaps. This shifts the emotional tone of discovery. Surprise becomes expected, confusion becomes productive, uncertainty becomes informative. As planetary science moves forward, it may adopt a more exploratory mindset, one that values mapping possibility spaces over defining final answers. The planet that breaks formation models becomes a waypoint in this exploration, marking a region where old maps no longer suffice. There is also a cultural implication for how science is perceived. Audiences often expect science to provide certainty. Discoveries like this challenge that expectation. They show science as an evolving process, responsive to evidence, willing to revise itself. This portrayal is more honest and ultimately more inspiring. It presents science not as a finished structure, but as an ongoing conversation with the universe. James Webb's planet does not shout its importance. It does not demand attention through spectacle. Its significance lies in its quiet refusal to conform. It asks scientists to slow down, reconsider, and expand their conceptual horizons. In doing so, it offers a reminder that understanding is not always about arriving at answers. Sometimes it is about learning how to ask questions that are worthy of the complexity they address. The planet does not close the book on formation theory, it leaves it open, and in that open space, between certainty and curiosity, between expectation and observation, planetary science finds itself not diminished but renewed. The universe, it turns out, is not finished surprising us, and perhaps it never will be. As this exploration reaches its final movement, the planet revealed by James Webb settles into a different role altogether. It is no longer simply an object of study, nor even a challenge to theory. It becomes a reference point, a quiet marker showing where certainty ends and curiosity begins. What started as a technical anomaly gradually transforms into something deeper, a lesson about how knowledge evolves when reality refuses to be simplified. By this stage, it becomes clear that the most important outcome of this discovery is not a revised equation or an updated diagram. It is a change in posture, a willingness to approach the universe without assuming it will arrange itself into familiar patterns. The planet does not undermine science. It refines it, reminding us that understanding is not a destination, but a continuous adjustment. For a long time, the success of planetary science depended on finding order. Order made the cosmos feel navigable. It allowed researchers to generalize, to extrapolate, to build coherent frameworks. Those frameworks were necessary, they were powerful, and they were built honestly from the best data available at the time. But James Webb reveals what happens when observational power outpaces conceptual comfort. The planet exists comfortably within the laws of physics, yet awkwardly within human explanation. That distinction matters. It shows that the problem is not nature behaving strangely, but our expectations being narrower than reality. The universe did not change. Our view of it did. This realization brings a kind of intellectual humility that is rare and valuable. It asks scientists to accept that some questions may not resolve cleanly, not because answers are hidden, but because multiple answers coexist. The planet's history may not be a single thread, but a braid. Several processes intertwine so tightly that separating them destroys the story they collectively tell. In this sense, the planet teaches restraint. It discourages premature certainty. It rewards patience. It invites scientists to sit with ambiguity without rushing to close it. That posture may feel uncomfortable, but it is a sign of maturity rather than weakness. There is also a quiet emotional shift embedded in this acceptance. Discovery is often imagined as a moment of triumph, a sudden clarity that resolves confusion. But some discoveries offer something different. They offer depth rather than resolution. They leave us with a richer sense of how much remains unknown, not as a failure, but as an invitation. James Webb's planet offers exactly that kind of depth. It reminds us that the universe is not obligated to tell us its story in the order we expect. It does not care about our categories, timelines, or conceptual boundaries. It evolves according to physical law, but within those laws, it explores a vast range of outcomes. Worlds form, change, interact, and persist in ways that do not always compress into simple narratives. This perspective reshapes how planetary science will likely move forward. Future discoveries may not aim to confirm existing frameworks, but to test their flexibility. The question may shift from, does this planet fit, to, what does this planet reveal about the range of what is possible? That shift is subtle but profound. It also reframes the role of James Webb itself. The telescope is not just a tool for answering questions. It is a tool for generating better ones. Its greatest contribution may not be the data it collects, but the conceptual space it opens. As more planets are observed with similar precision, it is likely that this one will no longer feel singular. Others will emerge that challenge assumptions in different ways. Some may contradict models of mass, others may defy expectations about composition or evolution. Together, they will form a landscape that demands a new way of thinking. In that future, this planet may be remembered not for how strange it was, but for when it appeared. It arrived at the moment when technology made ambiguity unavoidable, when it was no longer possible to average away complexity or dismiss contradictions as noise. There is also something quietly reassuring in this realization. It shows that science remains alive, that it still changes when confronted with evidence, that it does not freeze into dogma simply because a model has worked well for a time. James Webb's planet does not close a chapter in planetary science. It opens a slower, deeper one, a chapter where understanding grows not by narrowing possibilities, but by learning how to hold many of them at once. In a universe this vast, that may be the most honest form of knowledge we can achieve. And perhaps that is the final lesson of this discovery, that understanding the cosmos is not about taming it into simplicity, but about meeting it with curiosity, patience, and humility. About allowing it to remain larger than our explanations without letting that size diminish our desire to explore. The planet does not tell us that our theories failed. It tells us that the universe is still ahead of us, still offering worlds we did not expect, still unfolding stories we have not learned how to tell, still inviting us to listen more carefully than before. And in that invitation, quiet, unresolved, and deeply human, science continues, not towards certainty, but toward a deeper relationship with reality itself.